upon what we did in the last lesson when we solved a system of equations in 2 variables to now solving equations using 3 variables. So we need 3 equations with 3 variables where we're going to find what we call an ordered triple. Just like when we have 2 equations in 2 variables, we find an ordered pair. We're now finding 3 variables, so we need an ordered triple. There are some things that we can do when we're utilizing the Gaussian elimination method. It's extremely similar to the elimination method we learned using 2 variables. So some things with which we can do. We can interchange any 2 equations. So we can move them up, down, any order that we so choose to have them. We can multiply both sides of one of the equations by a non-zero constant, just as we did with the elimination method in lesson 6.1. We were able to multiply the equations by a value. And we can also add a non-zero multiple of one equation to another. So that's exactly what we did with the elimination. We added the equations together once we determined which variable we were going to eliminate, and we multiplied so that they found a common value that were just opposite yet the same value for their coefficients. We added them together so that we could eliminate that variable. So we're going to do the exact same thing here, except we only have 3 variables to work with. There are 3 options for the types of solutions that we could have. Since we're looking at 3 variables, we're in 3 dimension. So there could be exactly one solution where all of our planes intersect at a specific point. There could be infinitely many solutions, in which case our planes are intersecting on a line. Or no solution where all 3 planes do not have a common point or intersection. Right, our first example here is x minus 2y plus 3z is 11, 4x plus 2y minus 3z is 4, and 3x plus 3y minus z is 4. We can eliminate any variable that we want. We just need 2 equations in the same 2 variables in order to progress. I'm going to tackle eliminating the x variable. So to do that, I'm going to first look at my first 2 equations here. When I want to eliminate, then I know I need to multiply my first equation by not only 4, but a negative 4, such that when I add it to my middle equation, the x variables will disappear. Distributing through, I'll have negative 4x plus 8y minus 12z equals negative 44. Since the second equation already has the 4x, the opposite but same value for my coefficient, I'm just going to rewrite it as 4x plus 2y minus 3z equals 4. And then add these together. Our x variables will end up canceling, leaving me with 10y minus 15z is equal to negative 40. All right, now I need another equation in 2 variables. This time I'm going to look at the middle 2. I need to use 2 different equations in order to eliminate the variable. In this instance, I'm still going to eliminate x because I eliminated x out of the first 2. So when I look at my first and the second and the last, and looking at 3 and 4, I'm going to multiply the top by 3 and the bottom by negative 4 so that they're a multiple. Their common value would be 12, one a positive and one a negative. So distributing 3 across, I'll have 12x plus 6y minus 9z is 12. When I distribute negative 4, I have negative 12x minus 12y plus 4z equals negative 16. We'll add these together. Our x values disappear, and I now have negative 6y minus 5z is negative 4. Now I have 2 equations in 2 variables, and we can utilize the techniques that we did in lesson 6.1 to eliminate yet another variable. So I'm going to bring both of these equations down on top of each other so we can get a better look of what we might want to tackle. Looking at these two values, perhaps what might be easiest would be for me to multiply the second equation by a -3. So it looks like I'm going to eliminate my z value. When I multiply by -3, I'll have 18y plus 15z equals 12. Now when I add that to my 10y minus 15z equals -40, we will now have 28y, our z's disappear, equal -28. And now I can solve for y by dividing by dividing by 28, so y is equal to -1. So when I'm thinking about my solution then, my ordered triple, I know that my y value is -1. I still need to find x and y, x and z. What I can do then is substitute this y value into any one of the equations. Let's just choose this one since it's close. And notice then I'll be able to solve for z. So -6 times -1 minus 5 times z is -4. 6 minus 5z is -4. Subtract 6 from both sides gives us -10. So z is equal to 2. I now know that z is 2. We finally need to identify what is our x value. So I'm going to plug in y and z into one of my equations up above. Let's say I choose the first equation. Since x is already by itself, I'll have x minus 2 times -1 plus 3 times 2 equals 11. X plus 2 plus 6 is 11. X plus 8 is 11. So x is equal to 3. We have found our ordered triple. I have x plus y plus z is 7, and 3x minus 2y plus z is 3, and x plus 6y plus 3z is 25. I'm going to tackle eliminating my x variable, and I'm going to look at my first two equations. Looking at my first two equations, it appears that I only need to multiply the first equation by -3, such that when I add them together, my x variable will disappear. I'm multiplying through, I'll have -3x minus 3y minus 3z is -21. Bringing down that second equation, since we didn't need to multiply it by anything, and then adding them together so that my x variable eliminates, and I now have -5y minus 2z equals -18. I'm now going to look at my first and my last equation. Because notice that my first and my last equation here, they have the same value as our coefficients, only one would need to be multiplied by a negative value so that the x variable would eliminate. So let's do that. -x minus y minus z is -7. X plus 6y plus 3z is 25. Let's add them together. Again, our x variables eliminate, and I have 5y plus 2z equals +18. Now I have two equations in two variables. Let's stack them on top of each other and see what we might want to tackle for eliminating next. You may notice something right away here, that they're the same values, only the opposite number. So when I add them together, my y values disappear, my z values disappear, and my constants disappear. So I literally have 0 is equal to 0. This is a true statement, and since it's true just like it was if we had two variables, we have infinite maybe I could spell correctly. An infinitely many solutions. If we got to this point and we had 1 equals 0 and it was a false statement, there would then be no solutions. Let's take a look at an application problem. We're inherited $15,000 and we're going to invest it in a money market account, a municipal bond, and a mutual fund. After 1 year, we received $730 in simple interest from the three accounts. And the mutual fund paid, so the money market account paid 4% annually, the bond paid 5% annually, and the mutual fund paid 6% annually. We also know that there was $2,000 more invested in the mutual fund than in the bond. How much was invested in each category? So again, remember simple interest is interest equals principal times rates, the amount that we're investing times the rate. We have 3 variables here, 1 for each account. So let's let the money market account be X, let's let the municipal bond be Y, and the mutual fund be Z. So some of the things that we know that the percent of each one is 4% times the money market account. We know that we have 5% invested in the municipal bond, and then 6% times whatever is put into the mutual fund. Therefore, we replace them with their decimal versions from the percents. We also know that a total amount that we had invested was $15,000. So that when I add all the values that I put into the account from each one has to be $15,000. We also know that the interest that we have here per each account has to be $730. So 4/100ths X plus 5/100ths Y plus 6/100ths Z has to be $730. We also know, so therefore we have 1 equation and we have 2 equations. We know we need a third equation. The third equation comes from this part here, that there was $2,000 more in the mutual fund than the bond. So the mutual fund is $2,000 more than the bond. So the mutual fund is $2,000 more than the bond. So now we have a third equation. We've created our system of equations. I'm also going to multiply this equation here to eliminate the decimals. I'm going to multiply this by 100 so that I can get rid of those decimals. A little easier to work with whole numbers. We have X plus Y plus Z has to be 15,000. After I multiplied by 100, we have 4X plus 5Y plus 6Z is 73,000. And I also have Z is equal to 2,000 plus Y. I'm also going to subtract Y and just rewrite this as negative Y plus Z is 2,000. So it's set up very similar to the rest of them, where the whole number constant is on the right-hand side. All right, I'm first going to look at the first 2 equations because we know we're going to eliminate one of them. I'm going to multiply the top equation by -4, kind of sticking with the same technique that we've been doing by eliminating the X variable. You don't have to eliminate the X variable if you don't want to. I just find that it's useful. All right, when I eliminate the X variable, we'll need 4X minus 4Y minus 4Z is equal to negative 60,000. Adding that then to the second equation so we can eliminate that X variable. Our X variable is eliminated, and I have Y plus 2Z is equal to 13,000. Which is awesome because I already have another equation set equal to Y here. So I don't need to eliminate another one. We can line that up with what we have down here to continue eliminating a variable. And notice that they're already opposites. providing me with 3z is equal to 15,000. And when we divide, z is equal to 5,000. So we know the amount with which we have invested in the mutual fund. We just need to find the other values. Well, to find the other values, we can easily substitute z in for any one of those equations. So I'm going to replace z just in this one so I can identify what is y. So negative y plus 5,000 is 2,000, or negative y is equal to negative 3,000. Therefore, y is equal to $3,000. We now know that the part that we put in the bond is $3,000. Well, we know altogether it is $15,000. So when I take x plus 3,000 plus the 5,000 has to be 15,000. We know that x has to then be 7,000. I'll let you go ahead and double check to make sure that everything checks out. But now we found that there was $7,000 invested in the money market account, $3,000 was invested in the bonds, and then $5,000 was invested in mutual funds. The following table lists the number of civil cases pending in the U.S. federal court in 3 recent years. Use the data to find a quadratic function that gives the number of pending civil cases as a function of the number of years after 2009. Then let's use this function to estimate the number of civil cases pending in the U.S. federal courts in 2014. What we're doing here is finding a quadratic regression. Before, we would have to rely on Desmos by plugging these values in order to find the quadratic regression. Now we have some skills that we can utilize and find it algebraically, but certainly could use Desmos to help verify that what we found algebraically certainly works. We're particularly interested in what happens in 2014. So when I'm looking at this, I'm looking for 2014, which my value of x would then be 5. So we need to identify what value would fit into here. We know the 3 data points. We know 0, 30, about 31,000. We know the data point 2 with about 267,000, and 4 with about 300,000. We know that it's going to be quadratic in nature because it tells us so. So we know our general form of the quadratic equation is our value is equal to ax squared plus bx plus c. So when I'm first looking at my x variable of 0 and 31,353, I'll have a times, my x value is 0, a times 0 squared plus b times 0 plus c has to equal our y value of 311,353. Our zeros just all disappear here, so I'm left with c is equal to 311,353, which will be helpful here in a few steps. I also know 2 with 267,495, and we'll repeat this process with our value of x. So a times 2 squared plus b times 2 plus c has to equal 267,495. 4a plus 2b plus c equals 267,495. We also have the value for 300,469. So a times 4 squared plus b times 4 plus c has to be 300,469. Or 16a plus 4b plus c is 300,469. Well, I know what c is. We just found c. So I'm going to replace c both here and here so that we only have 2 equations in 2 variables. When I do that, then I'll have 4a plus 2b plus 311,353 equals 267,495. and 16a plus 4b plus 311,353 is 300,469. In both cases, I'm going to subtract the 311,000 here and bring it to the right-hand side so that all my variables are one side and the constants are on the other. That will then provide us with 4a plus 2b equals negative 43,858, and 16a plus 4b equals negative 10,884. Now that I have two equations and two variables, we can eliminate. I think it might be best to eliminate the a by simply multiplying my top equation by negative 4, so that I have negative 16a minus 8b equals positive 175,432. Now looking at these two equations, we can add them together. Our a value eliminates. We now have negative 4b equals 164,548. Dividing both sides by negative 4, b is equal to negative 41,137. So right now we have we have a b and we have our c value. We still need our a value. I'm going to substitute my a value into, let's say, this particular equation, one of our original ones, so that I can find our a value by substituting b. So I'll have 4a plus 2 times negative 41,137. Oops, I had too many 7s here when I was looking back. Equals negative 43,858. Or 4a minus 82,274 equals negative 43,858. Adding that 82,000 to both sides, 4a would provide me with 38,416. So a is equal to 9,604. We now have our a, b, and c for the general form of the quadratic regression. Our final equation here is then 9,604 x squared, our b value, so minus 41,137x, plus our c value of 311,353. Now that we have our function, we can use this to estimate the number of civil cases in the courts in 2014. So to do that, we just need to evaluate for our value of 5. So n of 5, when I replace all my x values with 5, it estimates at about 345,768, which when we look back at our data appears to fall in line appropriately with the values that are given. And this concludes our lesson on solving system of equations in 3